All right, so in this video, we're going to prove a theorem that basically says we can do u-substitutions. It's just, another example of a, like a technique of integration that we can now rigorously prove works using the fundamental theorems of calculus, okay? And like all of these kind of revolve around the basic theme of like, the reason that these techniques of integration work is just because we can actually just check that, if we have some function inside the integral and we have some expression that we believe should be the definite or the indefinite integral of that function, using whatever trick we use to like obtain that expression, right? Like with u-substitutions, it's like we have some function of another function u of x, and so we're doing sort of the backwards chain rule with u-substitution. So what we can do is basically just verify that actually going in the other direction, what we're claiming is the antiderivative truly is the antiderivative, because by taking the derivative, we obtain the thing that was inside the integral to begin with, right? And then it's through the fundamental theorem of calculus that we can actually use that to conclude that the technique of integration actually works when you're taking the integral, right? So I'll show you what I mean. So let's see. So here's the theorem. So theorem 34.4. Right, so let u be differentiable on an open interval I, and actually j, sorry, this one is j, and or well, such that u prime is continuous, right? Continuous, and let j be an open interval such that u of x is in j for all x in I. Or whoops, I flipped j and I again. This should be I, and this is I, and this is j. Right. So if f is continuous on I, then f composed u is continuous on j, and the integral from a to b of f composed u of x u prime of x dx equals the integral from u of a to u of b of f of u du. Okay. So this is for any a and b in j. Okay. So one thing I want to point out is just that in this theorem, we are not at any point integrating u or integrating f compose u over the entirety of the interval j. J is just kind of like this ambient open interval, so on which like all the integration takes place on like closed subintervals of that open interval. Okay, so I mean in practice this isn't an issue, because like in practice, if you're interested in some specific integral, you can always find like some open interval around that closed interval where all of these hypotheses are true. So yeah, that's just it's just a technical, kind of a technical detail of how they decided to formulate the theorem. But basically, right, what this boils down to is, so, okay, So clearly, f compose u is continuous on j. Yeah. Just because, so since f and u are continuous, right? So now fix c and I, then so we're going to basically take the indefinite integral of little f. So let f of s equal, I'm using a different letter because I think honestly, it's kind of strange. And in fact, I actually think that arguably, we should replace this u with something else too, but I don't know, whatever. So let's see. So capital F is just an indefinite integral of little f, right? So then, right, so then capital F prime of s equals little f of s for all s in I. That's by the fundamental theorem calculus 2. Right? Then let G be F compose U. Okay? So by the chain rule, G prime is F prime compose U times U prime. Right? So, and then capital F prime is just little f. So G prime of x equals little f compose U of x, U prime of x for all x in J, I believe. Yes. So then by the first fundamental theorem, we have that the integral from a to b of g prime, right, equals g of b minus g of a, and that's capital F of u of b minus capital F of u of a. Okay, so right here, and then if you go back to the theorem statement, right, the idea is that this is G prime inside here. So we're just doing like exactly what I said, right? This is the backwards chain rule. That's what u-substitution really is it's the backwards chain rule. And so the idea is that it's like if you ever have, and basically any technique of integration is effectively like a backwards version of some rule of differentiation, right? Some like either the product rule, the backwards version of that is like is integration by parts, right? Or the chain rule, the backwards version of that is u-substitutions and stuff like that, right? So pretty much, yeah. Any of those techniques of integration are basically like backwards versions of rules of differentiation. And so proving them is always just saying like, oh, well, if you just take this thing that you get from doing this like backwards rule of differentiation and then differentiate it, of course you're going to get the thing you started with, right? And then that means by the fundamental theorem of calculus that doing it backwards is correct, right? So here it's like, okay, we did this backwards one way, but then it's the same thing. So then also the integral from u of a to u of b of little f equals capital F. Right. Well, okay. I don't know. Let's write it this way. This equals the integral from c to u of b of little f minus the integral from c to u of a of little f. Oh, whoops. Little f. And this is capital F of u of b minus capital F of u of a. Right. So, this is the same, right? I mean, it's just the same. So now transitivity of equality shows us that. So the integral from a to b of g prime equals the integral from u of a. This is also why I really like avoiding the u of b. I like avoiding writing the variable of integration. They do it in the book, and I think they're doing that because it's like what you're used to seeing. So that's why they say like f of u du, even though we're already using u as the name of this function. So it's like, honestly, I think it's kind of abusive to like say f of u du in the integral because you're sort of overloading the symbol u. But yeah, I mean, honestly, I think it's a bit better to just, right. And then this is to just do it without the variables because it's just less clutter. This is the integral from a to b. Okay, and then in this one, actually, if we're gonna introduce, well, actually, this is the same thing as like, what was it? F compose u times u prime. Yeah. So yeah, that's u-substitution. So let's just do one little kind of a fun example with u-substitution. I think it's kind of cool, the one that they put here. So yeah, let g be 1, 2, 1, and differentiable on an open interval I. Then j equals g of I is an open interval. Again, remember, this is because if g is 1 to 1 and differentiable on this interval, well, then for one thing, it's continuous, right? So if it's 1 to 1 and continuous on this interval, then it has to either be increasing or decreasing, or strictly increasing or strictly decreasing, if you remember. And so then again, it's like not too difficult to show that if you have a strictly increasing function, then that will map an open interval to another open interval, or a strictly decreasing function will map an open interval to another open interval. So yeah, J is open, and G inverse, oops, is defined on J that's by theorem 29.9. So so what we'll show, so we claim, is that the integral from a to b of g plus the integral from g of a to g of b of g inverse equals b g of b minus a g of a. By the way, so if you're wondering where this comes from, let me draw a picture real quick. So here's kind of a graphical illustration of the fact that we're about to prove. And it's just saying that like these areas add up to what you expect them to, I guess, right? Which is that like the area under the curve here is the integral from a to b of g. And then the area over here is the integral, you know, between this curve and the y-axis, basically, that area is the integral from g of a to g of b of g inverse, right? Because remember that the graph of g inverse is just like the graph of g reflected across across the line y equals x. So we can think of, if we just like, you know, if we were to just reflect the picture, we could think of this as the graph of g inverse. And so, yeah, treating the y-axis as the x-axis, this area is the integral from g of a to g of b of g inverse, right? And so then those two add up to just be like basically the area of this big square minus the area of this little square. So the area of the big square is b g of b, and the area of the little square is a g of a. So that's where this, like, you can see where this formula comes from. And the proof they give is just this. So say f equals g inverse and u equals g in the change of variable formula. So so basically what we get is so the integral from a to b of g inverse compose u times u prime. So that's, and u prime is g prime, I guess, since u is g. So right, so this is f, this is g, or this is u, and this is u prime. This equals the integral from g of a to g of b of g inverse, right? That's this is just by the change of variables, so by change of variables. But then on this side, this also equals, so this is like x, right? Because this is just, you know, the identity function here. So if we put in a variable of integration now, this would be x g prime of x, sorry, x g prime of x dx, right? And then using integration by parts, so integration by parts, which I like to abbreviate IBP. So integration by parts with, specifically with I guess u equals x and v equals g, right? Then we get x g of x evaluated at b and a minus the integral of the integral of this thing, which is g, times the derivative of this, which is 1. So we get g from a to b, right? So that's b g of b minus a g of a minus the integral from a to b of g, right? So then what we see is connecting these two things, right? So here's one side, here's the other side. If you add the integral from a to b of g to the other side, right, to both sides of this equation, then you get exactly the formula that we claimed, right? So that does it for lecture 26. And thank you guys for sticking with it. It's been a pleasure. I hope that you all learned some valuable lessons about thinking analytically, and maybe a little bit of stuff about topology that might serve you well in the future in whatever sphere of or whatever area you end up finding yourself in. I genuinely believe that, you know, the material in this class can shape your thinking in ways that are sort of impossible to even identify or describe, but it'll help you think differently about the world in general. But anyway, yeah, so hope you enjoyed, and that'll be it. Goodbye.